Alright, looking at a sampling question involving an alkyne.
Yeah. That's not gonna work.
And it should be, mercury is on the bottom, but it should be in the top. And then H plus and water in there. So I don't know if I need to go through the mechanism. Should I go through the mechanism? Sure, why not? Okay. Number of carbons, 1, 2, 3, 4, 5, 6. Remember mercury has a lot of electrons around it, so we're gonna give mercury that lone pair. So what's my electrophile, what's my nucleophile? So mercury is still 2 plus, so that's still pretty delta plus, right, metal. And what about my nucleophile, what's it gonna be? The pi bond, right? So I know we've said before, H plus is a really good nucleophile, but you guys should recognize if mercury is in there, you're using mercury. Plus, this is 2 plus, that's 1 plus, use the mercury. So mechanism, pi bond attacks, same time lone pair comes back down and clamps down. Makes that mercurium ion. One, 2, 3, 4, 5, 6. Of course, this is a syn addition. Right, the mercury is adding to the one face, so both of these ethyl groups are going to be on the same side of the pi bond. Now at this point, we have this is itself a good electrophile, right? So mercury 2 plus. Water is a solvent. That can be a nucleophile. So add those lone pairs in there. Which carbon should we attack? 2 or 3? Or 3 or 4?
Doesn't matter.
Doesn't matter, right? Those carbons are exactly the same, right? Doesn't matter. This is a symmetrical internal alkyne, so 3 and 4 are the same carbons. In a C13 NMR, we'd have 1, 2, 3 peaks, right? Because this molecule has symmetry. So let's have water attack. I'm going to have attack 3. Okay, so electrons there. Shrink that down. Oops. So the pi bond. Now the mercury got electrons there, so now it's, instead of being 2 plus, now it's 1 plus. Ethyl. And the water. Now the water adds in such a fashion, right? What kind of addition is that? It's a anti-addition, right? Because the thing that added in the mercury are on opposite sides. We've balanced our charge, right? We start out with 2 plus. We end up with plus and plus, right? Notice how the mercury got electrons here, so it went to 1 plus. So still overall plus 2, still good there. What do we have left to do? We need to do replace the mercury, right? So mercury, again, is not very electron rich, so it's willing to give up. We'll do one thing first. Sorry. Before we do that, why don't we do a tautomerization? All right, 1, 2, 3, 4, 5, 6. Because if I was doing that before, I don't want to remake an alkyne. Right? Once you get rid of the alkyne, you're not remaking it. So I need to move the electrons here. What will that get me? Plus charge still on the oxygen. Mercury is still here. Hg1 plus. We added an H to carbon 4. Five. 6. Right, didn't lose a carbon yet. Now we're more prone to get rid of the mercury. Now we can get rid of the mercury. So now let's have the mercury leave. Electrons come down. Electrons go up. This is essentially, this was a tautomerization, right? This step was. And actually this step we just did is also like a mercury tautomerization essentially, right? We're taking a ketone and we're turning it back into a enol, right? If you look at it, what we're gonna do here. All right, that's an enol now. We just made an enol again. And the other resulting product, right, since we had plus one, we have to remake the mercury as, of course, a catalyst. So we're not done until we've remade Hg2 plus. But now at this point, this can tautomerize again, right? Taut. How's it going to do that? So we could either use the acid that's present to make it happen, or we could just do it without the acid. 1, 2, 3, 4, 5, 6. Let's do it without it. Forget it. Over there. And that turns it into a new H, back into a ketone, right? 1, 2, 3, 4, 5, 6. Okay. Made a ketone from mercury. We've regenerated catalyst, haven't lost a carbon. Did a couple, 3 tautomerizations, a syn addition and an anti-addition. One last question to actually answer this sampling question is saying one of these is a minor product, one of these is a major product. Which one's which?
Enol is the minor.
Enol is the minor. This is the minor product. Right? This is the major product. The way to remember this is acetone. Right? The stuff we use to clean our glassware in organic lab is a ketone, right? We call it acetone because it's a ketone. Because it exists mostly as a ketone. Maybe 1% of the time it's an enol. So usually the enol version, right? The enol version is not as stable as the ketone or aldehyde version. How do I know that? The simple delta H stuff. The CO pi bond versus the CC pi bond. A CH bond versus an OH bond. You can add up the bond energies, and this is more stable. So there you go. All right, take a look at quiz number 4 from 2014.
Oh, that's a good one.
Number 4. So this one shows acetylene, and it's saying several reactions, and you need to make this ketone. So this is retrosynthetic analysis. We got to work backwards. So we can first number our carbons on, let's number 2, 3, 4, 5, 6. Okay? So actually there's more than one way to do this one, for sure. There's actually another way to do this than I didn't draw on that actually answer key. So the hard part for this might be for you is saying, okay, you've numbered the products. I have no idea what numbers to do here, right? The best way to answer that is to say, okay, well, here's the ketone, right? There's the functional group. Where's the functional group at in there? Most likely, right? Carbon 2 is in here somewhere, right? So at this point, it's up to you how you want to do it, right? So you can either say this is 2 and 3, or you can say this is 2 and 1. It's up to you.
2 and 1.
2 and 1? Sure. 2 and 1. Okay? So that means if I take one step back, what was this one step back? What starting material did this ketone come from?
Alkyne.
An enol. And where was the pi bond at? Between which 2 carbons? 1 and 2. And that means the alcohol is on carbon 2. Good, very good. Now, what did the enol come from? What's the star material that makes enols. Alkynes, very good. And where will this alkyne be? Between which two carbons?
1 and 2.
1 and 2. Okay. Now, we should have also, in initial analysis, said something. What was one thing we should have said in our initial analysis when we looked at this to this? How many carbons does this starting material have?
2.
How many does the product have?
6.
Not more than 2. So what kind of reaction are you going to have to do? You have to make what kind of bond here? A carbon-carbon. How many ways do you know I make carbon-carbon bonds? Approximately 1, right? So that means you're going to need to, at some point, you're going to need to have a terminal alkyne, right, and deprotonate and make a carbon-carbon bond. So what carbon-carbon bond are you going to need to make here? Between which two carbons? 2 and 3. That's right. So I always like to draw these squiggly lines and say, okay, that's where it would be. So what would those starting materials be? It would be this alkyne, 2 and 1. And then we need that other carbon piece. And how am I going to make, right? Every bond we make, right? Every bond that's made, one part was the nucleophile, one part is the electrophile. In this case, which carbon is going to be the nucleophile? 2 or 3? In this case, which one has to be the nucleophile? 2 or 3? 2. So that means 3 needs to be the... And how are you going to make it delta plus? Because you can't just have a plus charge, right? How are you going to make it delta plus? Where else are you going to put on carbon 3? A bromine, right? To make carbon 3 delta plus, right, we need to put the bromine there, right? Or something else that's electronegative, right? Like an iodine or a chlorine, right? A polar covalent bond there. Good. So now, I think we're done, right? We've got to our starting material, right? So we've worked backwards, now we need to work forwards, right? So what reagents are we going to need going this way? What are we going to need to add going from these starting materials to form this product? What reagents are we going to need? Na, NH2, right? We're going to need a strong base. Na plus, NH2 minus. Good. Right? Because what's that going to do? That's going to, this N minus is going to deprotonate, well, I guess carbon 2. And that's going to put a negative charge there, and then this is going to attack carbon 3. You're going to make the 2 to 3 bond, right?
Water.
You don't need water. Nope.
You're making O, right?
Not yet, not yet. Okay, so everybody's there for that? So how am I going to turn my alkyne into an enol? You have a couple options here. What could I use to turn my alkyne into an enol? Mercury. Let's do the Hg2 plus in water. Right? That's going to give me that enol. If you chose BH3, what would happen? You'd get the anti-Markovnikov one, right? Notice this is also Markovnikov enol too. Good. And then the final step here, it's really just the tautomerization, right? You could add H plus to make it go faster, but there you go. Right, so the big take-home message is always be thinking about here's a ketone. What starting material did a ketone come from? Here's an enol. What starting material did the enol come from? Right, here's an alkyne with a new carbon-carbon bond. How do I do that? Right, you're looking at the products all the time. Look at the products and work backwards. Yep.
You said the Hg2 plus made it Markovnikov.
Hg2 plus would, or H plus would.
Okay, so
H plus would work too, but if I wanted to get an aldehyde and not a ketone, what reagents would I have used? BH3, step 1, step 2, OH minus, right? So that we know ways to turn a terminal alkyne into an aldehyde, not just a ketone as well. Right, if I wanted to make this an aldehyde, I could have done that too. But then it'd been a whole different thing though.
can you show how
Yep, absolutely. H plus and water could work as well. It's basically the same mechanism, right?
Not the H plus, but the.
Oh, the
Alkyne.
yeah. So we also could use H plus and water here too, right? Mercury is a catalyst, so that's one way. But what I'm talking about when I say, what if I wanted to get, let me shrink some of this stuff down. So let's pretend I was saying, instead of this product, what if I wanted to make this product? 1, 2, 3, 4, 5, 6. What if I wanted to make that product? Right? That would come from the same, that could come from the same alkyne, right? If I take one step back, right? If I take one step back,
Oh, it's a less substitute. Okay, I see now.
it would be this enol, right? Where the OH would be there. 1, 2, 3, 4, 5, 6. But it would come from the same, right? Where would the alkyne be at? The alkyne would still be between 1 and 2, right? It's the same alkyne. Right? If you switch reagents, you can get different products.
Yeah, there's no carbocation formation.
Right? There's never any carbocation formations. That's right. Right? So this alkyne and this alkyne are exactly the same, but switching reagents around. So what would the reagents be? You'd use BH3 in step 1, and then OH minus step 2.
Going from the, I guess, alkene to
The enol here.
the alkene to the alkanes, like, this is a different question.
Another good sapling question involved N-butyllithium, and it was reacting with a terminal alkyne, and the question was, so here are the products, they're telling you the products. And the question was what kind of arrows does this have? What kind of equilibrium arrows does it have? So the way to think about this, right, is to do some good analysis. So first of all, you should recognize when you see a lithium bonded to a carbon, that's really what kind of bond? What kind of bond is that? That's an ionic bond. So really, this carbon has a negative charge, this lithium has a plus charge. This carbon has a negative charge, this lithium has a plus charge. Good? Everybody with me so far? So what's the difference between here to here? How are you going to judge which way it should lie? So we're really asking which set of things is more stable. So if you don't know, let's look at what's different. What's different?
What is attached to the
You said right.
carbon with 3 bonds?
Because it's
What? Yep. So we're looking at,
This one carbon.
we're getting close. What's the difference?
Hybrid.
Hybridization state, where the electrons are at. Right? So here, carbon has a negative charge, carbon has a negative charge. So as we look at our periodic table and we say, well, which one's more electronegative, carbon or carbon? That's not helpful. Right? Right? We've done this before, right? We've done this before when we thought about stability of things from chapter unit 1. So what is different about these two carbons? They both have negative charges, but what is different about them? The hybridization state. Right? This is what hybridization state? sp3. It has 0 pi bonds, so it is sp3 hybridized. That means that negative charge, that lone pair, is in what kind of hybrid orbital then? What does it have to be in? An sp3? Right? There's an sp3. Let me draw that for you. Right? What's the hybridization state of this carbon? sp. Right? What hybrid orbital must that lone pair of electrons be in then for that carbon? Let's draw it. What does an sp orbital look like? Right? Remember, sp orbitals, right? This is me in high school, nice and skinny, tall, all the hopes and dreams in the world. This is me now. I'm fat, mostly p orbitals, right? But at least, you know what? When I was younger, I wasn't stable. Now, because I'm an sp orbital, I'm closer to what? The nucleus. And what, of course, is in the nucleus? Positive charged protons. So if you have a negative charge, you have electrons, would you want to be close or far away from the nucleus? Closer. So which one are you going to be happier in? An sp3 orbital and sp orbital? So which one's going to be more stable? This one. So where is the equilibrium going to lie? It's going to lie this way. All right, we're going to take a look at a multi-step synthesis, and then we're going to convert this to a free energy diagram. So the first step, we have a terminal alkyne. We have a strong base, Na plus, NH2 minus. What are they going to do? So this is probably going to be our nucleophile, right? It has a negative charge. In this case, it's going to be a particular type of nucleophile. What kind of nucleophile is it going to be? What kind of nucleophile is this going to be? It's going to take an H. That's what kind of nucleophile? Base. It's a base. It's a base. So it's going to deprotonate that. And our carbons, 1, 2, 3. So we've now turned carbon 3 into a nucleophile, right? Thank you, base. So let's see. Carbon 3 is now a nucleophile. One, two, three. So now we need to react it with an electrophile. So step 2 now, we're all done with step 1. Now we're on step 2. Let's have it react with carbon 4 here. Right, attacking sigma star of carbon 4, breaking that carbon-bromine bond. So now we've made a carbon-carbon bond. One, two, three, 4. Which is bonded to this aromatic ring. Right, and we've also made Br minus to balance our charge. Over here, of course, we made, there's an Na plus around. We also made NH3. That's all done with step 2. Step 3 is Lindlar's catalyst. What does Lindlar's catalyst do? It only has 2 hydrogens. And how does it add them? Syn addition. Make sure I don't lose a carbon. 1, 2, 3, 4. We added 2 H's. And that's it. Alright, so let's label everything. Starting material. We'll call this intermediate A. We'll call this intermediate B. And we'll call this the final product. Okay, so everybody's got a label. So now we're going to convert this into a free energy diagram. Now I think the easiest way to do this is to make your diagram, energy, reaction coordinate. I like to just fill it in before I put everything in. So my product versus my starting material. So my starting material is what? It's a alkyne. My product is what? Which one's higher in energy, alkynes or alkenes? Alkynes are. Very good. So let's put start material there, and we'll put product a little lower, right? Because it's an alkene. Good. So now we have, what do we have? Two intermediates? Intermediate A and intermediate B. Which one's going to be higher in energy? A or B? I think A will be, right? So A is going to be up here. And then B is probably going to be relatively stable, right? There's no charges on that. So it would probably be similar to the start material, actually. We added our transition state, our things. I think Lindlar's Catalyst goes pretty fast, but who knows? Right, so just kind of getting a relative idea about where things go, right? Alkynes are less stable than alkenes, right? Charged things are going to be high in energy, all those kind of things. Now in this case, to be careful, right? I'm just looking at the carbon species of each of these, right? If I was looking at this, right, this molecule right here, this benzyl bromide is stable, right? And in the starting material, NH2 minus is really reactive. So I'm just looking at this piece, right, the carbon pieces as I go, right? Because we just got done talking about where would this, if this was an equilibrium, this is an equilibrium arrow here, right? From here to here, where does it lie, do you think? Who's happier with the negative charge? Nitrogen or carbon? Nitrogen. So this shouldn't react, right? But it does. Why does it react? What's one of the byproducts? NH3. What's NH3? If you have an equilibrium reaction, how do you shift equilibrium? What are your tricks to shift equilibrium? What do? You add a bunch more start materials, or what else? What else could you do to shift equilibrium to products? How would you shift equilibrium? What could you do to get start materials to react, or to make sure they react, not go backwards? How do you make sure something doesn't go backwards? Right, this is an equilibrium. How do I make sure that this doesn't go back? What is NH3? It's not going to react with anything else. If you drove by a farm in beautiful Iowa and it smelled, what are you smelling? Methane and ammonia gas. NH3 is what? It's a gas. If one of your products is a gas, is this going to stay in solution? It's going to bubble out. Once it bubbles out, is it ever going backwards? No, right? Remember removing one of your products in an equilibrium reaction forces it forward? Right? It can't go back. If the stuff's not in solution anymore, it can't go back. Right? So if one of your products is a gas, that's what pushes this, right? Because normally you'd say, well, this won't react. Nitrogen would have a negative charge than carbon. You're right. But if this ever does react, is it ever going backwards? No. The gas will bubble away.